Thank you. So a major context that's been running through the conference so far has been that data scientists represent in and of themselves quite an expensive proposition. We're looking at a lot of these APIs that are specifically written to try and improve their productivity and thus improve the effectiveness of all of this money that's being spent in order to empower data science as part of your product workflow. Which means, if you are a living, breathing data scientist, you've got two things that you want to accomplish. One is you want to justify that kind of great expense that you personally embody. And two, you want to minimize the amount of your own personal time that's wasted. And on both of those scores, you can accomplish that by just growing the stack with which you personally are comfortable. And so this is going to be a talk today about some of my experiences as a data scientist at Upwork, moving more and more towards the implementation and system sides of things. Specifically, I think that the actor framework here that I'm going to discuss represents a powerful and simple way for you to start implementing at your firm some of these predictive APIs that we've started seeing at the industrial scale. So view this through the lens of somebody who's a grad student, someone who's a technical co-founder, someone who's the lone data scientist hired onto a firm that's just getting into this the first time, and think about what you could do to be more self-sufficient and how this actor framework represents a way for you to demonstrate greater value and greater productivity in your work, building these predictive models and predictive applications. So, I would posit that sometimes data scientists need to worry about throughput. Not all the time, but there are some circumstances where the throughput of your model, how quickly you can issue a new prediction, is important. One way to improve the throughput of your application is with concurrency. Stop doing these things in a kind of serial fashion and think of it more of a concurrent pipeline, doing more than one thing at once. The actor model is an easy way to conceive of and implement a highly concurrent system. And Scala plus akka is a language and a library that together provides a super easy to use implementation of that actor framework. And when you put these postulates together, I'm going to try and reach the conclusion that data scientists should at least check out Scala and akka. I think it would benefit your productivity, and I think you would enjoy it as a way of building the predictive APIs that we've seen used in a lot of these websites and applications in this conference. So data science, I think, was really helpfully broken up in two spots, even by Danny Lang in our opening keynote, in the sense that there is building the models, and then there's using the models. So there's lots of ways to get familiar with building models. You can start practicing on Kaggle contests. You can brush up on some Coursera courses. You can even get out to the vanguard and start building brand new models the world's never seen before, display them at NIPS, KDD, etc. And all of these share a classic process, which is to take whatever your data set is as raw materials and produce feature vectors from them. So represent whatever your original objects, your labeled objects were, and put them into this vector space. One set of these vectors will be used for training, another for validation, another for testing. Build the model using whatever your algorithm suggests over the training set, and then validate it, and then use the model on the testing set. So you can see right here, steps 3 and 4, building models, using models. It looks a lot like this when you break it into a block diagram where load all the raw materials, vectorize, train the model, and make test predictions. Build it, use it. You can even think of this now in a repeated testing context. So one way that you could use the model, even at an industrial level now, would be to repeat these first 3 steps: load, vectorize, train, build the model, and now use the model from some cached or saved flashpoint, a checkpoint. We saw that with the NVIDIA checkpointing, that every epoch a new model is being saved. Load one of those up, and then repeat just these processes here for repeated use of the model. Load up test or new materials, vectorize those, and then make the new predictions. And you would repeat this as needed every k minutes. So you can imagine for some applications like lead generation, say, this is going to work really, really well. You can run your e-commerce's data set through the algorithm to come up with a new model, and then test it on that day's new customers to see which are viable leads to send promos for particular products. So a lot of times my tasks work like that too, where you can get a kind of almost offline relationship between the use of the model. There's enough time here on this lag that serially loading, vectorizing, and testing to produce new predictions works just fine. Works exactly how you would do it for a Kaggle contest or a KDD paper. So this talk is about other kinds of tasks, where all of a sudden you do need to start worrying about performance. And remember, you're one person, and the more that you can incorporate a wide variety of capabilities under your belt, in your tool belt, the more value you're going to represent to society at large, and the better you're going to feel about your job. So sometimes data scientists need to worry about throughput, and an example for that is at my firm, Upwork. So we are a freelancing platform. People can come and post their resumes and pitch potential employers saying, please hire me through this website. Upwork will handle all of the payments processing, etc. Similarly, if you are looking to hire someone, a Java developer, let's say, you can post the job description online and then field resumes as they come in. And so we're kind of a matchmaking platform. And on both fronts, we have a search engine. You want to be able to search for a Java developer, we need to be able to show you Java developers. You want to search for Java application jobs, we need to be able to show you relevant jobs to that. So somebody posts a job, they then search for freelancers using our search engine, they find someone that they like, and they ask them to interview. And if everything goes well, that interview request is accepted. The freelancer that you reached out to likes what you had to say and wants to know more. That's a good outcome. A bad outcome would be, well, it just lays fallow. You reach out to this person and you never hear back from them. So the task is look at recent freelancer behavior. How has the freelancer been using the website recently? At time step 2, and then use that to predict whether they look like someone who's in the mood to accept an invitation to interview at time step 4. So if we have that kind of availability signal, we can use it to better improve the performance of the search engine. If you search for someone, we'll only show people who are liable to, or likely to, reply and accept your message. And that makes everyone happier. So building the model is business as usual. So load some raw materials up. So a whole bunch of examples of historical cases where a freelancer accepted or a freelancer rejected an invitation to interview. And then histories of that freelancer site activity immediately preceding that decision to accept or reject the interview. So that can be, how often in recent history has the freelancer been sending out their own proposals to work on other gigs? How many hours have they logged recently on the payment platform? The click logs that we have for the site, are they showing up a lot or a little? What parts of the site are they using? And then what kind of profile updates are they issuing? Are they changing their job description, adding skills, updating resumes and CVs or profile photos? So once we have this raw material, we can produce and vectorize feature vectors. And basically the approach that I took was just to train on month 1 through 8 and test on months 9 through 12 as a kind of validation that indeed we can predict what someone looks like right before they're going to accept versus reject an invitation to interview. And then we train and evaluate the model through just a simple A/B testing interface was what we used. We tweaked the search engine so that we would only promote people who looked available, and we got some very pleasant results back. When we tilted towards people that this signal said was available, we actually got much higher responsiveness, which was good. So we have to recognize here is this magic step right here. That's kind of been given short shrift in a lot of the presentations and a lot of the cases and tutorials that you see online on how to be a data scientist, which is that we've got this raw data that we need to vectorize, and it lives in a diversity of spots. You know, we use a Greenplum system to host the work logs and the job applications. We use S3 to bundle up those massive amounts of click logs that we generate every second of the day. And then we've just got our own internal service that provides information about profile updates. And so all of this is raw material that needs to be harnessed and gathered and polished and turned into these vectors in step 2. So when we use the availability model, it looks exactly like it looked before. The only problem is now we have to talk about how often we're repeating this. And in terms of availability, we need this to be a pretty short and tight loop. 60 minutes, I think, is even pushing it. Because the last thing we want is for someone to accept a job and still get flooded with a bunch of new requests. You know, if this is only refreshed once a day, that's a day's worth of invitations that went out for, you know, to no avail, falling on deaf ears. So the tighter we can make this loop, the better the model's going to perform. Because when we were looking at things historically, we had the benefit of hindsight. We could pretend, you know, that we had exact information at the time of like, this is what they looked like, because we could retroactively fill in their behavior. And when we want to simulate that now, or we want to re-implement that now, when it comes to live testing, the quicker we can make this loop, the better. So that means loading, vectorizing, and then making the actual prediction themselves, running the model itself, all has to happen in a fairly tight loop. So when we talk about what that entails, you know, we need to make a Postgres call to load job application data, to load work hours data. Each of these takes, you know, a 4 to 5 minute return on the kinds of volume that we're looking at. The click log data is a big slog through Amazon S3. Text is streamed in over a network connection. That's 30 minutes. And then the real bottleneck here is the internal service that provides profile data, which I'm going to say takes 20 milliseconds per profile. For each profile you make, there's just some latency for that service to reply. Our internal API has a rate limit that I don't want to violate. So if we think about that bottleneck right there, what we're implicitly saying is that, well, we've got less than 21 minutes to do this part, given what we subtracted away with the S3 and the Postgres requests. So just getting the raw data leaves us with 21 minutes for this. So that's at most 63,000 profiles that we can refresh per hour. So if we want to keep everyone's little score, their availability score, as fresh as possible, we're only going to be able to do that for 63,000 people in this hour. People who get to have their score refreshed, you better hope that you've got one of those lucky tickets to be one of those 63,000 people. You know, we can do some triaging. We can make sure that people who've recently updated their profile or have recently done job searches go to the top of this queue, but fundamentally we've got a supply constraint here. And it's really irritating to worry about, you know, the fact that this 20 milliseconds of profile is limiting us to 63,000 people on a platform that, in all honesty, has 6 million different freelancer profiles, any one of which at any time could become active again, or could be exactly the freelancer that, you know, employer X is looking to hire. Which means that about 90 hours would go on average, with 6 million people and 63 profiles an hour, 90 hours between each refresh. That's a huge amount of time to consider, just in the expected value case, before you would ever get a chance to plead your case and say, no, I really am available. Like, we don't get to you if we're stuck with this. And the reason that 63,000 comes out of this is because we're spending so much time on these parts first. So this is even just ignoring the time spent actually building and exporting the scores. And I think that at this time scale, we can fudge that down to the milliseconds to seconds range. It's not that hard to actually do the raw computation once the data is in memory. So if we want to increase throughput, one way we can think about doing that is by implementing this not as a serial system of load the apps, load the work hours, load the click log, and then start hitting the profile service, but increase that throughput with concurrency. So an expensive option, and I mean this in a relative sense, a relatively expensive option would be to make some pretty severe demands of infrastructure. So we've got these highly concurrent systems that are all the rage: Apache Spark, Apache Storm, Kafka, all have been touched on, and they really are, I believe, the best that money can buy in terms of getting highly concurrent systems up and running. But it requires a lot of time, attention, and cooperation. So again, put yourself in the shoes of the first data scientist joining the firm, the lone technical co-founder, you know, the grad student working in a research lounge. Like, that kind of time, attention, and cooperation might not be available, or might be prohibited. Like, it would be really weird for me to take a job and say, like, oh, sure, I can get you a predictive API for $5 finding available versus unavailable freelancers, but step one is I'm going to need you to break out the checkbook and buy me a $10,000 cluster. If I can find a suitable framework that reaches similar performance that I can do myself as a data scientist, I've demonstrated much more value and I've saved a lot of time and heartache, especially if we're talking about something that may yet be unproven. If I'm just trying to develop this as a prototype or a proof of concept, having something that's midway between the old school read files in and out of the file system and the bleeding edge Spark, Storm, Kafka, I personally would find a lot of value in that as a data scientist. And that's exactly what I'm going to describe here. The actor model is a model of concurrency that makes it very straightforward to think of how doing a bunch of things in parallel or pipeline would work. It's something that takes advantage of, or basically splits the Gordian knot of what makes concurrency hard. And basically what makes concurrency hard is shared mutable state. If you've got two things working at once and they both contend for the same resource, if one of them is writing while the other one is reading, you can wind up with all kinds of problems of false sharing. And so the way that's split in the actor model is to kind of break the shared part. There's still shared mutable, there's now mutable state, but it's all privately held. So the core of the actor model are these little abstractions called actors, which you can imagine as just a mailbox with a brain. Computation only ever happens if a message shows up in the mailbox. Otherwise, the brain just sits there insensate. And the brain itself keeps its thoughts private. It's got a whole bunch of private state up here, its own memories, what it's keeping track of, that it only conveys to the outside world or to other actors via this message passing. It all happens asynchronously, and there's no way for someone to ask directly, hey, tell me right now what is the availability of this contractor. Instead, what they do is they pass a message in, and the availability of that contractor is responded to when the message comes up at the top of the queue. So there's a mailbox that fills up with messages from other actors that get responded to. Lots of actors, each with their own queue and their own private state, all living in the same execution context, which is an implementation that allows for handling the routing of the messages, the actual implementation of the queues themselves, and resource sharing. So making sure that if you've only got 4 CPUs but 16 actors or 16 million actors, that whoever needs to do computation right now, that handoff of resources happens as efficiently as possible between them. And now the important thing, the thing that makes concurrency simple to reason about, is the fact that each message's computation is fully completed before the actor moves on to the next message. So you can even imagine having some messages that come in that say, hey, update your state, I've got new click log data. That update happens to 100% completion in an almost transactional way before the actor moves on to respond to the next message, which may be, hey, what was the click log data for user X? So there's no more false sharing or contention because it all gets linearized at, I'm sorry, that's a very loaded term for database people. It all gets put into a certain order by the asynchronous message queue. So there's no sharing of state except by this message passing, and the execution context makes sure that the computations involved with each message happen in a very transactional way. And so you can see this now as all of these little brains with mailboxes sending a bunch of messages back and forth, each with their own tiny specified task. And it gives you, almost like object-oriented programming lets you very easily decouple major problems and break them down into small problems. This kind of approach to concurrency lets you take what seems like a huge system, well, I've got a load from all these 17 different data sources, and break them down into one actor each of which is very easy to reason about, and each of which is whose computation is taken care of for you by the execution context. So when I talk about the actor library, ACA, what I'm really talking about is the implementation of these actors, and then more importantly, the execution context they live in. So when we parallelize the exact same model usage that we had before for availability, we take each of those boxes that used to be a serial process and make each of them a concurrent actor. So we've got one up here that's responsible for refreshing work hours. And it gets a little message from the execution context once an hour that says, hey, if you're not busy, please refresh your work hours now. And that sits in their queue until it gets to the top. And once that happens, it thinks, oh, great, I've got a message asking me to refresh work hours. I will go make the Postgres call, and when that comes back, I will have completed the task. Once that task comes in, it can send a message to the vectorizer that says, I've got new work hour data, and the vectorizer can receive that message and say, thanks, I've now updated my own private state of what I think the work hour logs look like. So we've got a decoupling here where one actor is constantly getting the freshest possible data about work hour histories, and then another actor has its own possibly stale versions of that. But the important thing is that this one is free to only update when it gets a message, and similarly, it can handle, oh, we've got an update about the job applications, or we've got an update about the S3 click logs, or we've got an update about profile information. And so you can have this one conductor that's just, all it's doing is keeping its local copy of what each user's behavior looks like, each freelancer's behavior looks like, and it only has to update that when it gets actual messages saying we've got 2 wins. So what we had before was this idea that a serial task that took forever, leaving us only 16 minutes to do the actual fetching. Throughput was around 48 users per hour under these calculations, if we spend 5 minutes on the vectorization. If you think about this now in the concurrent sense, this is all pipelined. And what beautifully happens is that the execution context can make sure that one actor is constantly fetching this profile information, which gives us a throughput now of 180 users per hour. So before, we were only fetching profiles for just this tiny window of the serial processing, but the concurrency gives us, basically fetching profiles and throughput that happens 24 hours a day. So Scala and akka provides an easy-to-use actor model context. I can provide links to this later. The message passing schedule and computation behavior is all defined for my actor system in 445 lines, something that I wrote in an afternoon. All you have to do is inherit this actor trait and implement this method that says if you receive a message, respond to it appropriately, and then you just have to do your own business logic reasoning of what it means to respond to I've got new work log information. So this is going to show up online. It'll be less of an eye chart there, but here's just floor to ceiling, one entire actor. It's not that hard. There's just mixing in the interface and implementing it, some private mutable state for storing the scores that need exporting, the last time an export happened, and then 2 case studies of if you receive a particular message, how to respond to them. If new scores are coming in, hold on to them. If you're scoring a lot of them, upload them out to the place where the scores are supposed to be stored. And then if told to shut down, just stop accepting anything new until the context is canceled. So the pros are, I think that it's a very productive language to be in. I think very important is that the Java bytecode that Scala compiles down to allows you to do all of your dependency management in one place. So you can compile this entire system down to one fat jar and put it on any machine off of AWS that has the same Java runtime. Very, very simple compared to something like Python Ruby Node, where it's hard to get your packages managed appropriately. I think that dependency management is very straightforward in this. And most important of all, on a technical level, Scala and the JVM, no global interpreter log. So you can actually make use of the multi-core machines that you're renting from your hosting provider in a way that it's hard to make happen with Scala or Ruby, all with the same process and thus same shared virtual memory space. And the cons are that, well, there's a moderate Scala learning curve. I got into it mostly because I liked using Spark. And now that I'm in it, I'm deep in it. But I could understand why somebody would have trouble ramping up on that. Object representation on the JVM is very lousy when it comes to memory efficiency. If I can throw some shade, I don't mean to stir the hornet's nest too much on that, but compared to something like NumPy or C or C++, these are very large representations of what should be very simple, very simple floating point arrays wind up taking much more space than you would think. And finally, I would say that right now, it's getting better every day, but there's not a lot of great options for building the models themselves in Scala compared to your R ecosystem, your Python ecosystem, your Juliet ecosystem. So in conclusion, we started with the postulate that sometimes, for some tasks, a data scientist needs to worry about throughput. Concurrency is a great way to increase throughput. Actor models are a great way to reason your way into building what is traditionally hard to build, a concurrent system. Scala and akka is a very lightweight way to implement actor systems, actor frameworks. You put them all together, and I would recommend that if you are a data scientist or on the verge of becoming one, think about using Scala and akka when it comes time to build a predictive API for your use case. So thank you very much, and I'll take questions.